little bit early, but we're live for the moment. We'll have 5 minutes or so. Technically, it's supposed to have 5 minutes, so they could start sooner. But if I do come late, might feel like they missed out on something. Of course, if you guys have any questions, feel free to ask. All right, so it's 8 o'clock now, so hello everybody. It's Mr. Arocena, and like I mentioned in class today, I'm going to go over parts of the solubility equilibrium review that I gave you guys after you completed that quiz. I haven't marked all the quizzes yet, but I will have them done for you guys by tomorrow. Giving everybody a different quiz really slows down the marking a bit, but I think it helps you guys out a lot more. All right, so like I mentioned, I'm not going to go over all of this. Some of the stuff you can pick up from the textbook by reading it. Like for example, this one here, describe the equilibrium of a saturated solution. I think the definition of a saturated solution is right in your textbook. Similarly, describing what permanently hard water is, that's also in your textbook too, I think. But this next one here, what is the net ionic equation between this? Let's answer that one. Because for whatever reason, in my experience, this question always seems to confuse a lot of students. So the net ionic equation is, again, let's grab it. So we have Li 2s, and we are combining it with PbNO32, so that's lead 2 nitrate. And this will break down into the following ions: Li plus, sulfur 2 minus, Pb2 plus, and NO3 minus. And of these ions, if a precipitate forms, that's where we'll take the net ionic equation from whatever precipitate forms. So in this case, I think, to the best of my memory, it's going to be the lead 2 and the sulfide combining together. And these two will form lead sulfide. Okay, so the net ionic equation will just be whatever forms this low soluble salt. So the net ionic equation will just be Pb2 plus S2 minus, forming that. So that would be my net ionic equation. Okay. So that's net ionic equation, and that's really all there is to it for that. You just have to determine what the low soluble compound is, and then figure out what ions combine together to make that low soluble compound. There's really not much we can really vary on this question other than possibly throwing down several solutions together. So a variation of this that you might see on your test would be something like we mix together several different solutions. So take, for example, lead nitrate, throw down some silver nitrate, and we add in there something like ammonium carbonate, then maybe something silly like ammonium chloride. So if you throw in something like this where we have, because here we have 4 different salts, same kind of rule applies. We just separate everything into its ions. So we have lead 2 plus, we have nitrate. I don't have to list the other nitrate because I'm just interested in listing the ions out. We have ammonium, and then carbonate, chloride. Now we just see what combination of ions will result in low soluble compounds. So for example, like the Pb2 plus and the CO3, that will result in a low soluble compound. So I can write a net ionic equation for that compound. The silver and the carbonate, same thing. So the silver carbonate will result in a low soluble compound. So I can write a net ionic equation for that. The lead chloride will be another one, PbCl2. That'll be a low soluble compound, so I can write a net ionic equation for that. And then the AgCl will also be one. So in this particular mixture, I would have 4 different precipitates forming, so I can write 4 different net ionic equations. Okay. That's really the only variation I can kind of do on this question, is just throwing in more stuff at you. And I think if I remember correctly, one of the quiz variation questions had a solution where we mixed a bunch of things together and you were asked to find the precipitate. Although I think some versions of that quiz had everything. I think everything was soluble because they were all alkali metals or nitrates, and there was none that would actually precipitate. So if you get a situation like that where nothing actually precipitates, then there is no net ionic equation because nothing actually forms. All right. Now this next one here is actually kind of easy, the correct KSP expressions. So if you remember KSP, It's just really a variant of products over reactants. So, but with solubility equations, we tend to start off with the reactant. So what's our barium sulfate? So barium sulfate will have this formula, barium sulfate. And when we want to write the KSP for this particular equilibrium, when this goes into solution, this will create barium ions and sulfate ions. It will be aqueous, this will be aqueous, this will be solid. So when I write my equilibrium expression for this, I will get the following: concentration of barium 2 plus, concentration of SO4 2 minus, all over top of the concentration of barium sulfate, and that'll be solid. Now, because the barium sulfate is a solid, we don't actually need that, or I can actually remove the whole thing because it's a solid. So the KSP equation or expression just becomes the following: Ba2 plus times SO4 2 minus. And there you go. And this would be the equilibrium expression. It's actually quite a bit easier than the KEQ equations we were working with in the previous unit, because the reactant, it can be ignored because it's just solid. Okay. So with that said, the copper sulfide and the silver chloride, their KSP expressions will look like this. So copper 2 sulfide, copper 2 sulfide will be Cu2 plus and then S2 minus, like that. And then the other one was silver chloride, so KSP will be silver and chlorine, like that. Yeah, so those are the KSP expressions. Now, if you are given a salt, for example, like silver carbonate, this when it goes into equilibrium will form 2 parts silver and 1 part carbonate. So when it is put into the KSP, we have to take into account that we've got 2 silvers, so KSP will become Ag2 plus squared times CO3 2 minus. Okay, so the square comes from this coefficient here. Okay. Now, once you have this equation, we can then use this equation to calculate the equilibrium concentrations of the salts. That's what the next question asks. So in question 5, calculate the equilibrium concentrations of each salt. In question 4, this is a very big assumption we make, because if we don't start with a solid chunk of each salt and instead we start with some amount of sulfate, this question actually turns a little bit easier. Do I have an example of that here? I do not have an example of that on the review, but I have my textbook with me, so I'll pull it out and I'll show an example of when you don't start with a solid chunk. I'll show an example of that later. All right, so I'll start with the barium sulfate. So barium sulfate has a KSP equation of barium 2 plus and SO4 2 minus. And according to our textbook, the KSP of barium sulfate is 1.1 times 10 to the negative 10. That'll equal the concentration of the barium sulfate times the concentration of the barium ion times concentration of sulfate. Where do we get this? Well, from that we can sort of write down the equilibrium equation. This Ba2 plus SO4 2 minus. If I have an unknown amount of this, it'll dissolve into equal unknown amounts of that and that. So we can say the following, that the barium has a concentration of X, sulfate has a concentration of X. That can really just simplify to X squared. So this is 1.1 times 10 to the negative 10. And then X will just be the square root of that, 1.1 times 10 to the negative 10. Okay. And then we can take that X and then we can put it into the concentrations of these. And that'll be the concentration of our salt. And then same process for the other ones. So copper sulfide, I think, will give effectively the same kind of steps. The only difference is the KSP for copper sulfide is different. So for the copper 2 sulfide, same thing. We have the equilibrium expression, 2 plus, 2 minus, and then copper 2 sulfide has a KSP of, wow, that's really small, 6.0 times 10 to the negative 37. Through similar logic as the previous one, I'll just write it down here. Copper 2 sulfide will turn into 1 copper 2 plus, 1 sulfide 2 minus. So this will just, again, similar equation. It'll be an X squared. Square root this to get rid of the X, or the square, sorry, whoops. Get rid of the square, and that'll be your value for the concentration. Now things sort of take a slight turn for the worse, I guess, if you end up having a salt like this, silver sulfide, yeah, so like this. If you have silver sulfide, this is what caused a bunch of confusion I think it was last week. Yeah. Which hopefully we all sorted out now. I hope so. I hope we all sorted this out. Anyways, so the in this situation, the concentration of the silver will be 2x and the concentration of sulfide will be x. So when this goes into my KSP expression, this will be 2x squared and this will be x. So this ends up being 4x squared times x. So this will be 4x cubed. And then silver sulfide, sadly do not have the KSP value for silver sulfide in our textbook, so I'll have to make note not to use that for your tests. But same kind of idea applies. Let's say for argument's sake, let's say the KSP for this is 1 times 10 to the negative 10. Then we just do a bunch of algebra to get for x. So divide both sides by 4 and then cube root it. And that will get rid of this. That'll get rid of this, and then x is whatever this number happens to be. So be mindful of that. If you have salts that that have this kind of behavior, you can even get really crazy. I don't think there's anything in your textbook that has anything super crazy. See now, no, everything is either. Yeah, everything is either all just, everything will have the form AB going to A plus B, or it'll be something like this, where it goes to 2A plus B. So everything will either just be X's, or it'll be a 2X and X. We don't have anything where we would have something like this. Although if we did, that wouldn't be too terrible, because this just ends up being some solving as follows, and then this would just end up being 3x, this would end up being 2x, and the KSP for this will be whatever it happens to be. So KSP for a form like that, you would get what, 3x cubed, 2x squared, and then the algebra just ends up being a little scarier than what we were dealing with prior. So, but we don't deal with this type of salt. We don't deal with that. We don't deal with that kind of salt in Chem 12. It's just a lot of extra algebra we don't really need to do at this moment. All right. So that was basically question 5. All right, question 6. Here it asks us what mass of barium sulfate will dissolve in that much water, and we're going to assume a saturated solution. So we'll take the barium sulfate. Take the barium sulfate. I'm going to quickly write out what its dissolving equation will be. Barium 2 plus sulfate 2 minus. This will turn into X amounts and X amounts. That's good. I'll write out my KSP expression. Concentration of barium 2 plus times concentration of sulfate 2 minus. And then barium sulfate, I have the KSP for that. It's 1.1 times 10 to the negative 10 equals x squared, because these are all x's. Okay, so this will allow me to calculate what the x is. X will just be the square root of 1.1 times 10 to the negative 10. This also happens to be the concentration of the barium 2 plus and the concentration of the SO4 2 minus. Now, one thing this also allows me to figure out is, by extension, the concentration of the barium sulfate. Okay. Now, that's important because this question is asking me for what mass of the barium sulfate will dissolve in some amount of water. So if I know the concentration of this, and remember concentration, so the concentration of barium sulfate is moles of barium sulfate over volume of barium over volume. Then if I know what X is, then I can take this and put it into this number here, and I can calculate the moles based on what volume I have. So let's see, barium sulfate is concentration is square root of 1.1 times 10 to the negative 10. I can calculate the amount of moles based on my 250 milliliters that I currently have. So the total number of moles will then end up being 0.25 liters times the concentration, which is 1.1 times, or sorry, square root of 1.1 times the negative 10. And that'll give me moles. Okay, we're not done yet because we don't want moles, we actually want mass. So now it's just a simple calculation to go from moles to mass. So once I have the mole amount, I can take the mole amount and then I can multiply it by the molar mass of barium sulfate. And that'll end up giving me grams. Okay, so I've kind of intentionally left the numbers out so that you guys can do it yourself. But all the steps are there for you to follow. Okay, and hopefully the process is understandable, hopefully. Okay, this will be left up anyway, so you can go back and watch it again. But yeah, so this, I should make a note that this quantity here is the molar mass of barium sulfate. All right. Okay. So variations of this question, just basically change the salt, change the volume. Process will pretty much be the same as far as what you would see on your test. Okay. That was for number 6. All right, number 7. This one requires a little bit more thought, I want to say. This requires a little bit more thought. Yes, because we are mixing some amount of silver nitrate. We're mixing it with some amount of sodium chloride. All right, so to do this question, we need to first, so from the silver nitrate AgNO3, we have 50 milliliters at 0 0.001, yeah, 001. This will allow us to calculate the following, and there are, I guess, kind of two trains of thought for doing this. I was noticing that, I guess the best way I can put it is, might be a little confusing to try to use just one method. That's not the way I want to put it. You know what? I'll just show you what the preferred method you should use. Okay, because this, if you do it this way, if you do it the following, then it'll be a lot better. For it, it's a more robust method, I guess. Robust method meaning that it'll work in every situation and you don't have to worry about any weird exceptions. So what you want to do first is calculate the moles of silver, or moles of each ion in this, from this salt. I'm not sure if I explicitly stated this when I first went through this particular section. If I didn't, then I can understand the confusion. But for now, this is actually probably the preferred way of solving a problem like this, because it'll work no matter what formula the salt takes. So the moles of silver you can calculate as follows. We can take the concentration of the silver nitrate, and then we can multiply it by the 50 milliliters. Now notice I'm not changing my 50 milliliters into liters. If I do this calculation, this will give me a unit called millimoles. Okay, so when I carry out this multiplication, I think I get 0.05, and this will be in a unit called millimoles. Okay, I'll do the same thing here. This will be 0. Actually, I don't even need to do this calculation again. The 1-to-1 ratio of silver and nitrate means that this is just going to be 0.05 millimoles. Okay, so that's the first salt. Now we do the same thing for the second salt. The second salt was sodium chloride. Oh, that's stupid. I should have said sodium nitrate, whatever. Sodium chloride. In the sodium, oh jeez, I totally forgot what. 50 milliliters, 0.005. Okay, so 50 milliliters at 0.0005 molar. So the same thing, calculate moles of Na, calculate moles of Cl. I only need to do one calculation because I have a 1-to-1 ratio, so this should be really easy. So there's my concentration multiplied by my 50 millimole or 50 milliliters. This will give me 0.0025. That'll be the same thing for the chloride ions. Okay, so now that I've got the mole amounts, I guess in this case millimole amounts, I can then go ahead and calculate the concentration of each. So pull this down. All right. So slide this over a bit. So now when we calculate the concentration of the silver in the mixture, the concentration of the silver, the new concentration, will be 0.05 millimoles, and we'll divide that by the new concentration, which is the 50 plus the 50, so the 100 millimoles. This will give me a concentration of 0.0 0.05, I think. I'll be in molar. I want to check because I'm not confident. I'm not confident in myself. I think that's right. I think that's right. 0.05 divided by 100. Yeah, okay, good. Okay, there we go. All right, so there you go. Now I have the concentration of the silver, and because of everything being 1-to-1, that will also be the same thing as the concentration of the nitrate. 5 molar. And then we can do the same calculation here. So the concentration of, right, boom, slide over this way. So the concentration of the Na plus will be 0.0025 divided by 100, and my cat is stuck in my chair. There we go. Okay. Bye, cat. All right. Yes, so this will end up being 0.000025. That's a really small number, which will also be the concentration of the chlorine minus ion. Yeah. All right, so there you go. So this is how you can calculate the ion concentrations of each ion. Okay. However, we're actually not done yet because that's not what the question's asking. The question is asking, will a precipitate form? Does a precipitate form? Okay, that's what the question's asking. But in order to answer that question, we have to calculate the ion concentrations. Why? Because two of these ions might combine to make a precipitate. Okay. You guys can probably guess that already, which two ions will make it, but if you can't, we'll check. Well, we already know the nitrate won't because nitrate's always soluble, so we check sodium or the chloride ion, and it turns out that silver chloride will form a low soluble precipitate. Okay, so at equilibrium, this will be, wait, silver is only 1 plus. Silver's only 1. The silver 1 plus chlorine minus, like that. There we go. And so we have to check. So the KSP will be based on silver ions and chlorine ions. Okay, so these are the ions we want in question. So I'll highlight these. So the silver ion has this concentration. The chloride ion has this concentration. So we'll create a test quotient product called Q, and we'll multiply those concentrations together. So 0.0005 for the silver, and then 0.000025 for the chlorine. And then we just carry out that multiplication, and you will get a ridiculous number. This will be 5 times 10 to the negative 4 times 2.5 times 10 to the negative 5. So this will end up being, see, 5 times 2.5 gives me 12.5 times 10 to the negative 9. So this is 1.25 times 10 to the negative 8. Alright, so there's my trial ion product. Alright, now we check what is the actual KSP of silver chloride. Okay, so KSP of silver chloride is 1.8 times 10 to the negative 10 to the negative 10. There's the actual KSP. There's our trial ion product. Q is greater than KSP, so a precipitate will form. A precipitate will form. There we go. There. So quite a lot of calculations for this question, because one, we had to calculate the ions present. or the concentration of the ions present, and then we had to calculate the trial ion product. Okay, now pay attention to the technique I use to calculate the ion concentrations, because that is very handy when you want to calculate the ion concentrations of a mixture such as nope, not that one. Let me pull it up quickly. So yeah, like this one. So this question here, if you calculate the moles first, so here, like, calculate moles of each ion, then concentration. It's a much more robust method, and it'll work in situations where you have multiple sources of the same ion, like in this question. Because like in this question you have both salts provide nitrate ions, but one salt provides twice as many nitrate ions as the other. So if you calculate the moles of the nitrate, then you can calculate the total number of nitrate moles that are present, and then just use that to calculate the concentration of nitrate ions. You don't have to worry about fiddling with any kind of ratios or anything like that. Anyways, on to the next question in the review. All right, so here we have a solution of strontium, silver, and carbonate, or not carbonate, that's calcium. We add this 0.01 molar potassium carbonate drop by drop. What are the possible precipitates that could form, and which precipitate would form first? So this one is really just to see if you actually form carbonate precipitates, which I think you do, because carbonate precipitates everything. So you'll end up with strontium carbonate, silver carbonate, and then calcium carbonate. And then we just check what's the KSP of each of these values, or sorry, each of these salts. Remembering that KSP is a measure of how soluble something is, or basically KSP is a measure of which side of the reaction, or which side of the dissolving equilibrium, solubility equilibrium, is favored. If KSP is large, so KSP, large KSP favors that side, whereas low KSP favors this side. So basically low KSP is more on the solid side of things, large KSP is more on the aqueous side of things. So just compare numbers. So strontium carbonate is 5.6 times 10 to the negative 10. Silver carbonate, is that it? Yeah, silver carbonate is 8.5 times 10 to the negative 10. And calcium carbonate is 5.0 times 10 to the negative 9. So, wait, did I mess up somewhere? Oh, silver carbonate should be not to the negative 10. Silver carbonate should be to the negative 12. There we go. All right, then just check which one is the smallest. This one's the smallest. So this one will form first, followed by this one, and then this will be the last one to form. Okay. And interestingly enough, you could actually use this fact to, if you're careful enough, you can actually use this fact to separate these ions by carefully adding the proper amount of carbonate to precipitate each one by itself. Actually would be a really neat question. Oh, cool. All right, next. Okay, oh yeah, this is kind of a misleading statement. I really should get rid of it, because you don't actually have to do any calculations. All you have to do is just compare numbers, which I guess in a way is its own calculation. Alright, last question, number 9. Describe 4 ways you can increase the solubility of calcium carbonate. Remember, oh, this is actually, there really isn't too much to this, and I really should not say 4 ways, because the 4 ways are kind of silly and they're really just one way. Alright, so here is the dissolving equation. Again, this is solid, this is aqueous, this is aqueous. Okay, so one way we can increase the solubility, and this one I will allow it, is raise temperature. So admittedly, if this is one of those weird salts that is the opposite, where raising the temperature actually reduces solubility, then that would be not a good idea. But for now, we'll assume that it's endothermic reaction. So raising the temperature will actually increase solubility. That's one. Okay, other ways, reduce this. But you have to be specific about how you do it. So you can precipitate carbon out with, and this is where you can actually finish your question just by listing 3 different things that you can use to precipitate the calcium out. So you could use something like lithium carbonate, or lithium phosphate, or lithium sulfite. Yeah, sulfite, yeah, 2, there we go. Oh, I could even probably also use lithium hydroxide. That would work too. Basically, any 4 salts that will provide an anion that that the calcium precipitates with. But it has to be a salt. It cannot just be an ion, because those ions have to come from somewhere. Okay, so if you answer this question by just listing the ions, you will not get full marks for it, because we need a source for those ions. Okay. Admittedly, you can also probably do something like rubidium carbonate, because rubidium is also, or ammonium carbonate, or yeah, I think you get the idea. Similarly, you can do the same thing with this one. You could say you can precipitate the CO3 minus with, I don't know, lead nitrate. Not the best idea because lead's dangerous. Lead nitrate would work. Copper nitrate, strontium nitrate, basically any metal nitrate that's not an alkali metal will precipitate the carbon out, or carbonate out. There you go. Yeah, so like I said, for this particular question, the 4 ways is kind of like just use 4 different salts. Temperature change, 4 different salts, and that'll work. Alright. Really good question. I'll have to remember that. Anyways, so that does it then for the review. If you guys paid attention to that, that's great. Like I said, this will be up. I'm not going to take it down, so if you did not see the whole thing, you can go back and watch it. If you watch it in double speed, it'll only take about 20 minutes. Haha, but I sound really funny in double speed. Anyways, for those of you guys watching, if you have any questions, just type it into the chat, what page and what question number. I have my textbook with me today, so I can actually look it up and answer it. Oh yeah, I forgot about Discord. I should make a Discord for my class. Then you guys can just question 62, 61, and 62. From our oops. Okay, 61 asks, or does a precipitate form when we have the following 25 milliliter, or wait, 25 milliliters of 1.0 times 10 to the negative 4 molar of zinc nitrate. Okay, and then we mix it with 45 milliliters of 2.0 times 10 to the negative, wait, negative 5. Oh, that's interesting. Calcium hydroxide? What an odd. Strange. I'm just assuming the calcium hydroxide completely. Oh wait, that's neither here nor there. I have the concentration of the calcium hydroxide. So the calcium hydroxide should dissolve into 1 part calcium, then 2 parts parts hydroxide, like so. I have the concentration of this, so even though we know that the calcium hydroxide is low soluble, will still dissolve appropriately. So this will be 2.0 times 10 to the negative 5, and this will be 4.0 times 10 to the negative 5. So that's the multiplying by 2. The precipitate that forms from the zinc, zinc will turn into zinc ions and then nitrate ions, but we don't care about the nitrate ions. The ones we care about will be this and this. So that will form this precipitate, zinc hydroxide. Okay. So then our KSP will be as follows. Zinc plus 2 OH minus. I have the concentration of the OH. The zinc I can pull from. Oh wait, but I'm mixing them, aren't I? Yeah, okay. So I have to actually calculate stuff. All right. Wait. First, like I said before, calculate the moles of OH. That would be 4.0 times 10 to the negative 5 molar times 45 milliliters. Yeah, 45 milliliters. Oh wait, I messed that up. Let's read the question. This should be 2.4. 2.4, so that makes it 4.8. Okay, not too bad. 45 milliliters, that'll give me some amount of millimoles. .8 to the 4.8 exponent of this 5 times 45, so I hate this calculator. 4.8 exponent 5 times 45. There you go. Okay, so that's how many millimoles I have. 0.00216, 0.00216, and then concentration of OH will be 0.00216 over shoot, 45 plus 25? Yeah, 45 plus 25, that's 70. So, 70. A small concentration, 3.1 times 10 to the negative 5. 1 times 10 to the negative 5. And then repeat the process for zinc. So, moles of zinc. Yeah, moles of zinc would be its concentration of 1 times 10 to the negative 4 times 25. So that's 2.5 times 10 to the negative 3 moles or millimoles. Concentration of zinc, 2.5 times 10 to the negative 3 over 70. Oh, I did that wrong. 5 divided by 70. 6, we'll say. Okay, and then multiply those two together and check against the KSP. That one should be no. I think. Yeah, and then the KSP equation, once you have that. Yeah, okay, so that should be right. So KSP will then be concentration of zinc plus times concentration of OH squared. That. And those two numbers. Yeah. And then that should give you what, oh sorry, not KSP, Q, because we're checking the trial ion. And then compare that to the KSP. Okay, now what's 62? What's the difference about 62? In 62, yeah. So in 62, the question is very similar. Let's see, so we have 100 milliliters of 4.0 times 10 to the negative 2 molar calcium chloride. Then we have 150 milliliters of 2.9 times 10 to the negative 2 molar NaOH. Okay, and then just last, you multiply the concentration of OH by 2. 61, but they don't in 62. Oh, that's because okay, that's because similar to what I was mentioning earlier, just calculate the moles of each ion. So we know that the calcium chloride will provide calcium ions according to this. We don't care about the chlorides because they're not the interesting one. And similarly in the NaOH, this will provide sodium ions and hydroxide ions. We don't care about this, we don't care about that. All we care about is this and this. From the CaCl2, use a different color for this. From the CaCl2, we can calculate the moles of Ca. And then from the NaOH, we can calculate the moles of OH. And we don't have to multiply by 2 because even though the calcium hydroxide is formed from 2 OHs and then the resulting the resulting equilibrium looks like this, we don't have to multiply by this 2, because this situation is not a result of calcium hydroxide dissolving. This equilibrium arises from we're getting a bunch of calcium and a bunch of hydroxide being mixed together to force this equilibrium. So the two situations are slightly different. Okay, in this case, all of this hydroxide, that's what'll form the concentration here, and similarly all of this calcium is what forms the concentration of calcium here. So if I take my moles of hydroxide from the sodium hydroxide, that's the fixed number of moles, and then from that'll allow me to calculate the concentration. So let me just do that quickly. Let me rewrite all of this. Okay, so from the NaOH, I can calculate the moles of OH as follows. Moles of OH will equal I have concentration of 2.9 times 10 to the negative 2 molar times 150 milliliters. So this will give me the following. So wait. Oh yeah, sorry, milliliters. 4.35 millimoles. This will be 4.35 millimoles. And this is how much hydroxide I have. Now the concentration of hydroxide will be the 4.35 millimoles divided by the total volume, which is 250 milliliters. That'll be divide by 250. So 0.0174, 0.0174 molar. I think is right. Yeah. There you go. So now we don't actually need to multiply this by 2 anymore, because we already have the concentration. This is the concentration. We don't have to worry about multiplying by 2x or anything like that. So I hope that clears up that one. And then if we finish the problem, we need from the I just lost the question. We need concentration of calcium. So from the calcium chloride, we can calculate the moles of calcium as follows. Moles of calcium plus will be 4.0 times 10 to the negative 2 molar times 100 milliliters. So this will be 4 millimoles. And then the concentration of calcium, the calcium will be the 4 millimoles divided by 250 milliliters, which will end up being 4 divided by 250, 0.016, 6 molar. There we go. Okay. And then I think the question's asking, yeah, what's the KSP for? Oh, hey, we can use this to calculate the KSP of calcium hydroxide, despite it not being in your textbook. Cool. And the KSP equation for this particular, because that's what the question is asking, is what is the KSP of calcium hydroxide? Well, KSP just ends up being concentration calcium 2 plus times concentration of OH minus, but squared, because calcium hydroxide is 2 there. There you go. And then we have the concentrations, a simple math fact of multiplying those two together. All right. Hopefully that clears things up. That one is actually kind of a tricky question, but like I mentioned near the beginning of this, not near the beginning, at some point in tonight's stream, I mentioned that when you're doing these ion type calculations, do this. It will save you a lot of headache if you just calculate the moles of the ion first, then calculate the concentration after that. Then it'll work. It'll work much nicer. Way more robust method, I think. It does. In some cases, it can lead to like a few extra calculations, but I think overall it makes a lot more sense if you calculate the moles first and then the concentrations after that. All right. I think I've been on long enough. If you guys have any questions about any of the assignments or whatnot, yeah, come find me tomorrow. Your test is going to be on Thursday. We have our double blocks, so you guys can have both blocks to work on it. Right, it's getting a little late, so get some sleep, and we'll see you in class tomorrow.